we'll get started. It's recorded anyway. So this is actually a pretty quick PowerPoint. We're doing chapter 7 and chapter 8. Chapter 7, range equation. This is kind of us finishing up the pulsed sound wave that we were talking about last week. So we've learned all about sound, how we describe sound, how we monitor sound, and then we kind of took it a step further and we said, okay, well now if I put these sound waves together, I can send that in as a collection, right? And that's how we get our pulsed sound wave. That pulse sound wave is really important for us because we send that into the body and then we wait for those reflections to come back to us. So that's kind of like the meat and the potatoes of how we're creating our images. So chapter 7, range equation, this is really just talking about the specific time that it takes for that pulse to get where it needs to go and then to come back to us. So they like to give you math questions on the registry for this. Just remember that there is a 13-second micro rule that goes with this, and we'll get to that on our next slide. But basically the time of flight, also known as the go return time, that's exactly what it is. How long is it taking for that pulse that was created in our transducer to get where it needs to go and then to also come back to us? So we're looking at that total travel time. So time of flight, it's exactly like if you're going on vacation somewhere, right? You want to know how long is it going to take you to get there, but then we also want to know how long is it going to take you to get back home. Usually should always be the same amount of time to get there as it takes you to come back. So we're just calculating that. The time of flight is going to be directly related to our depth. So of course, as we increase our depth, we are going to be increasing that time of flight. It's going to take us longer to send that pulse into that reflector position and get it back to our transducer. So our shallow imaging, right, we're looking at something superficial. We're going to have a very short time of flight. So again, if you're going to Florida, you're going to have a shorter time of flight or go return time than if you're going to Hawaii. So you can actually calculate your time of flight. The main thing with this is you want to be aware of that microsecond rule that we'll talk about in a second, but you can take the average speed of sound to calculate this. This is a little bit harder than what the registry will probably ask you, but just be aware of this equation. If you have like a cheat sheet of equations going on, definitely add this to it. Now, as we know also with using the average speed of sound, we know that bone is going to have a ridiculously higher speed of sound, right, than air would. So we're using the average speed of just regular soft tissue. We're not really looking at those minute differences between liver tissue versus muscle tissue, right? They're all kind of in the same ballpark. So we're using that as our average. So here's our 13-second micro rule. So this is always going to apply when sound travels through that average soft tissue. And basically, we've kind of come to the conclusion that every 13 microseconds, that object can travel 1 centimeter deeper into the body, or that object can be located 1 centimeter deeper in the body. So for every 1 centimeter, we have this average 13 microsecond go return time. So this means that the time it takes to get to that object 1 centimeter into the body and come back to us is going to be 13 microseconds. So we can use this as the basis to figure out how much further something is in the body, or depending on if we've given that distance, we can figure out how long it's going to take us to get there and get back. So 13 microseconds is going to be an object that's located 1 centimeter deep, means that this sound wave has traveled 2 centimeters total, right? Because if it's positioned 1 centimeter deep in the body, 1 centimeter to the object, 1 centimeter back for its total travel. So here's just a nice little visual diagram showing us that distance as we expect that pulse sound wave to travel. And as we get to that 10 centimeters into the body, we are at 13 times 10, so 130 microseconds there and back total. So kind of still going along with that time of flight or that go return time, we need to take into account our PRP. Anyone remember what that stands for? Good. Okay, just making sure. And we want to be able to say, okay, how long is this going to take me if I want to go X number of centimeters into the body, right? So our PRP, or pulse repetition period, that's the time from the start of that pulse in our transducer, as soon as we send it in, to the start of the next pulse. So we're taking into consideration that pulse duration, how long it takes that pulse to travel and do its thing, but then also we are taking into consideration all of that off time, that listening time, and that is going to be our PRP. So the PRP is the go return time of a sound pulse between the transducer and the bottom of the image. So wherever we have our depth set is going to be our maximum when we're talking about our PRP. So this is going to be directly related to our depth. So as our depth increases, right, we're looking deeper and deeper into the body, our PRP is going to increase, right? So usually our pulse duration is going to stay the same, but now we're going to have more listening time the deeper into the body that we're looking. So that is going to make our PRP increase. So an increase in depth also means an increase in go return time, therefore an increase in our PRP. So for an example, if we have our depth set at 10 centimeters, that 10 times 13 microsecond rule is going to be 130 microseconds of PRP. It would be half of that for a depth of 5. So what would be our total travel if our depth is set at 5 centimeters? What would be the total travel? Good. So next we have our maximum depth, or the depth that we are setting our image at, and figuring how that is going to affect our PRF, our pulse repetition frequency. Anyone remember what pulse repetition frequency is telling us? Not the distance that it takes. That pulse is going to stay the same, right?
It's like for something that's 1 second or 1 second.
Yes, the amount of pulses that we can send in a given period of time, typically 1 second, right? We measure that in hertz, but we are saying how many cycles or collections of pulses can we send in per 1 second. So if this example is giving us a time duration of 1 second, what would our PRF be?
Yeah.
So if this is saying, okay, this is our duration of 1 second, what would our PRF be? Good. Little refresher from our last few PowerPoints. So unlike PRP, our PRF is going to be inversely related to that depth. So if we are increasing our depth, we're decreasing our PRF, right? So we are saying that because we are sending in more waves into the body, we have more listen. We're not sending more waves. We're increasing that depth that wave has to travel. We need more listening time, so we're not going to be able to send as many pulses in that 1 second time frame. So when our depth is shallow and we have that superficial imaging, that's when we can talk and talk and talk and talk and talk in that 1 second time frame, because we don't need as much listening time when we have that shallow imaging. And then vice versa, when our imaging is deep, our PRF is low because we have to listen more. So it takes longer for that to happen. Therefore, it's going to be decreasing the amount of cycles or pulses that we can send in. So again, you can calculate this. You can, actually, we'll get to this in a second, but go to our next one here. Hold on, I feel like I'm missing a slide.
On the 2 slides with PRP and PRF,
Yes.
next step, do you have pictures?
Yes, I'll upload the newer version. So we're still on this slide here. So basically, going back to this first bullet point, in 1 second, sound can travel to and from a depth of 77,000 centimeters. And that's because if we are using that average speed of sound in soft tissue, that 1,540 meters per second, if we convert that into centimeters, right, because we're using centimeters in ultrasound, we're not using meters, we're not using inches. If you convert that 1,540 meters, you get 154,000 centimeters. So where are we getting 77 77,000 centimeters from. So if you convert 150, right, we're dividing it in half because remember, we're taking that distance into consideration. So it can travel 154,000 centimeters per second, but we need to say, okay, well, that's there and back, right? So we have to cut that distance in half. So that's where we're getting that 77,000 centimeters from. Now, 77,000 centimeters is pretty big, right? So for that pulse to travel in 1 second, that's super fast, right? We don't need that in imaging. So now we're going to convert that to a range that we typically use. So 7.7 centimeters into the body, that's pretty much right where our liver is going to be positioned, our kidneys are going to be positioned. So that means it can travel to 7.7 centimeters 10,000 times in 1 second. Now this is where we get that fast imaging from. We're going to learn about frame rate in a few weeks, but that's what we need. We need to be able to send that pulse into the body and get it back thousands and thousands of times to get our very detailed pictures. All right, so that's kind of finishing up the sound properties that we've been talking about before. Now we're going to be moving a little bit more into the clinical aspect, and we're going to learn about transducers. I do want to preface this by saying that this is very basic information about the transducers. This is not talking about transducers specifically. We know that we have different types of transducers for whatever exam we're performing, and we will get to that, but this is mainly just talking about the basic composition of transducers. So as we know, transducers are going to be any type of device that can convert one form of energy to another. So for us, we're taking electrical energy from our machine, and we are asking that transducer to convert that electrical energy into acoustic energy. Now, there are a lot of processes and steps that go beyond that, but we basically need certain materials in order to make that happen. So yes, we use transducers mainly in ultrasound, and that's probably right where your mind goes to, but there are really all other types of transducers out there. There are probes of every sort that can convert electrical energy into heat or convert electrical energy into sound. That's not an ultrasound transducer. So kind of keep that in the back of your mind too as we go through this very basic chapter of transducers. So for us, we are expecting that transducer to perform two functions. We want it to transmit. This means we are taking the electrical energy from the actual ultrasound machine and we are converting that into our acoustic energy. And then we're also saying that we need that transducer to be able to process those reflected sound waves, right, that reflected acoustic energy, and then convert it back to electrical energy. So it needs to be able to perform those two functions. Yes, it has to convert energy from one to another, but then it also has to do it in reverse. So there are a lot of properties that go behind getting that to happen. So the main thing with the transducer, particularly for ultrasound, it needs to have a piezoelectric effect. And this is when we have certain materials that on a very cellular and organic level have these certain properties that when we apply energy to them, we apply mainly voltage to them, they're going to be able to deform or change shape. So this is something that's a very bizarre concept because usually you have one object or one material, and that usually is what it is, right? But some materials are very sensitive to any type of energy applied to them, that because of that application of voltage, it's going to change its own composition because of it. And then we also want to be aware of what is known as the reverse piezoelectric effect. And this is mainly talking about those materials that actually change their shape when that voltage is applied to them. So the piezoelectric effect, that's going to be when they start to deform, when that pressure or that energy is applied to them. And if they actually change their shape, that's the reverse piezoelectric effect. So we need an ultrasound, because we are saying to our transducer, I want you to convert electrical energy to sound energy and then vice versa. We need to have those materials that are able to deform and kind of change themselves when we are applying voltage to them. So those are going to be piezoelectric materials, also known as ferroelectric materials. This means that they're able to do that. They're actually, ferroelectric is also known as dielectric, and this means that it can do two different things in terms of converting electricity. So this is exactly what we want when we're making our transducers. Some of these materials are going to be naturally sourced. So quartz, tourmaline, these are all naturally found rocks and crystals that have this composition to them that are able to convert different types of energy. So if you know anyone who is big into like crystals or healing, quartz is always a big one with them because it's actually converting energy. So, you know, on a very cellular level, some people can feel that or use that for restorative purposes. So a lot of these materials are going to be naturally sourced, but for us, we want to have more of a consistent regulation of this conversion of energy. So for us, we're using mainly synthetic materials and lead zirconiate, titanite, I don't know. This is going to be the most commonly used material on a synthetic level that we are putting in our transducers. Now, with the sources that occur naturally, that conversion of energy is going to happen spontaneously. We don't control it. We're not manipulating that. But for us, we need to be able to have that consistency. So these synthetic materials, that conversion of energy is not going to happen spontaneously. In order for us to get that conversion to happen, we need to apply that voltage to it to get it to deform. And then we also need to apply heat to it. So those are the two circumstances that we need for these synthetic piezoelectric materials. Now, heat is a very sensitive subject when it comes to transducers. We want to heat up that piezoelectric material in the transducer only to a specific point, and that's the Curie point. That is the maximum temperature that we can have applied to our piezoelectric material in the transducer, but it's also the temperature where that conversion is going to take place. So it's a very precise and particular heat temperature in order to get this reaction to occur, but also to not go over it. When we go over that temperature, that is when we can produce damage to the material. And of course, it's not going to be beneficial to us. So on that same topic, when we're cleaning our transducers, we've now learned that this piezoelectric material, this is really the important part of our composition of our transducer, and we don't want to apply too much heat to it. So how are we going to be cleaning our probes, right? We want to be aware of that. Now, you may have seen in hospitals, or you may have worked in certain situations where surgical tools are put in an autoclave, right? That very high temperature sterilization process. Would we put a transducer in an autoclave? No, because that's going to go way beyond that Curie temperature, and it's actually going to damage that piezoelectric material in the transducer. So what we need to do is just levels of disinfection. Not just levels of disinfection, but we don't really ever want to be using sterilization, especially heat sterilization with the transducer. We're also not using transducers invasively, meaning like in surgical processes without taking steps to protect the transducer and also the patient. So what we're doing mainly with some of our more sensitive transducers like the transvaginal probe or the transrectal probe, we are putting that in high levels of disinfection. You may have seen this at your clinic site. This is Cydex solution. So basically this chemical solution that you are putting the probe in is a very high level of killing all types of organisms. And then you may have also seen this out at clinical as well. This is what is known as a trophon, and it uses heat below that Curie point, and it also uses UV to kill the microorganisms. So for some of our more sensitive transducers where we need to do more than just a wipe on it, we're using either Cydex or a solution or a trophon to disinfect. We are never sterilizing. So now we're going to talk about that basic construction, and your textbook goes into depth about every single layering component of the transducers. So please make sure you go over that. We do have it on our next slide, the page number that all of that is on. But we're basically, when we're talking about the construction of the transducers, they're very, very complex, although they share similarities with single, simple, unfocused probes. So this is what we're going to be using as our example. When we get into the specifics of each type of transducer, that's when we're going to take it a step further, and we're going to talk about the differences between the makeup of those probes. But on a very basic level, we are talking about just probes in general. Remember, probes is anything that can convert one type of energy into another. So this is a picture of an oscilloscope. So that is going to convert heat into electrical energy. So this is going to be the same type of concept that we are talking about when we're talking about our simple transducers. So just keep in mind that not every transducer or every probe is only used for ultrasound. So a basic transducer is going to have the appearance of a cylindrical tube. That's how the majority of our components and materials are layered in the transducer in a cylindrical tube. The sound pulse is going to be emitted from the front of that tube, which is going to be placed on the skin of the patient. And then there's a wire connection from the back of the transducer to the system. So that's how we're connecting our sound source to our electrical source. So very basic with that. So here, this is actually right from page 115 in your textbook. So make sure you go through the chart that they have on page 115. We're going to talk about each of these components today, but if you need further clarification, you can definitely reference the textbook. These are, there's 7 main components to a simple transducer. So we have our case that's going to protect everything, the patient, the transducer. We also have an electrical shield, so that's going to make sure that we're not shocking our patient, right? Because we're converting that electrical energy into our sound energy. So we want to make sure that we're keeping everyone safe. We have an acoustic insulator, which we're going to be talking about. We have our active element or our piezoelectric material. We have our wire, which is connecting that to our electrical source. We have our matching layer, and we have our backing layer. So this probably looks a little bit more familiar to what you guys have learned so far. That previous slide, you're probably like, well, where is that tube located, right? It's just a very basic diagram. This is a little bit more realistic as to what you guys are used to seeing. And if you looked at the transducers last week, you can actually see each of these layers and components kind of stacking on top of each other. So you guys can look at these later today too, if you'd like. So we're going to be talking about today mainly the backing element. We've already talked about the piezoelectric elements, those active elements, and then also our matching layer. We're going to learn about our acoustic lens when we learn about the specifics of each transducer. The acoustic lens is something that is put in transducers to help them focus, right? So how do we focus our sound beam? So that's something that we'll learn a little bit more about. It's not really one of the main components of a transducer because it's a little bit different for each type of transducer. But every transducer in ultrasound is going to have a matching layer. So whenever you guys go to scan each other and you put the probe right down on your partner or on a patient, what happens? You pick up the probe, you put it right down. You don't see anything, right? Why? You didn't put gel on it. So gel is needed because of the matching layer. So we learned last week about impedances, right? That resistance that the sound beam encounters as it's traveling through soft tissue. Well, we're treating these components of the transducer as tissue, right? Because we're expecting sound waves to travel through them. So we need to be aware of how they behave. So our matching layer is basically going to provide a middle ground impedance between the skin's impedance and between active elements impedance. So basically, when you put down that transducer without gel, the impedances are so great that it's going to produce this massive reflection, right? So it's not sending any sound waves into the body because all the sound waves are being reflected right back into the transducer because the impedance difference is too high. So that wave can't travel into the body, right? So it's almost like hitting a wall and saying, all right, I got to turn around and go home. So when you're putting that transducer on somebody without the gel, you are just getting that massive reflection back to you. Nothing is being transmitted into the body because of that. So the impedance of the piezoelectric material or the active element or crystal is 20 times greater than the impedance of the skin. So that's a pretty drastic boundary for that sound wave to have to travel through, and it can't. So that's why it just reflects itself right back. So if sound travels directly from the PZT to the skin, the majority of that sound wave is going to reflect back into the PZT. Only a small fraction would transmit, resulting in extremely limited clinical imaging, and that's why we're not getting any type of diagnostic picture. So our matching layer provides this particular amount of impedance in between that active element and the skin, so that it's decreasing the amount of reflection that's occurring at that boundary, and it's allowing for some of it to continue traveling. Now, the same thing happens between the matching layer and the skin, right? So the impedance between the matching layer and the impedance of the skin is still too much of a drastic boundary for that sound wave to travel through it. So that's why we need gel. Gel is that middle ground impedance between the matching layer and the skin. And that's why it allows that sound wave to travel in, because not as much is being reflected at that drastic boundary. Next, we have our backing material. So this is kind of a bizarre concept. If you're a little confused by what the backing material does, that's okay. The textbook is also kind of makes it a little bit more confusing. So don't think about the backing material too much. What we're basically doing with this is we are reducing the free vibration of the sound wave. So we're basically saying we have this sound wave that's produced in our transducer, and it wants to go off and sing and do its own thing. We're basically saying, no, like you can't sing that loud, or you can't sing that song. So we're giving it limitations to what it wants to naturally do. So when we have these high frequency transducers and we are sending in these pulses of these sound cycles, they want to go crazy, right? They're excited, they want to just vibrate and have all of the natural frequency that they want, but that's not great for our image. So we need to kind of tone it down a little bit, and that's what the backing material does. Also known as damping material, and that's exactly what it's doing to that sound wave. So it's going to optimize the pulses that are created in the transducer, and without that backing material, that active element or that crystal is going to vibrate longer than it should. And we don't want that, because that's going to mess with our pulse duration. That's going to mess with our PRP, our PRF. We don't want that. So the backing material is going to keep those pulses nice and short, kind of like just a piano key, right? You're just striking a piano key and that's it. So if the PZT vibrates for too long, the pulses are going to have an increased length and duration, resulting in decreased resolution and accuracy, which we know we do not want. So there are certain characteristics of backing material. It has a high degree of absorption, so it's going to absorb all of those lingering frequencies so that it doesn't vibrate for too long. And it's going to have an acoustic impedance similar to the PZT, so it is still going to allow those pulses to move easily from that active element, that PZT, to the backing material, where it's going to be absorbed and kind of, given instruction on what it can do. Now, there are some consequences of having backing material. So yes, we don't want our sound wave to just vibrate uncontrollably or longer than we need it to. But when we're adding this backing material, we are affecting other things negatively. So we're decreasing the sensitivity, right? So we're basically saying you can't be as strong as you want to be because I'm going to dampen you. So we're having a decrease in sensitivity from this backing material. We are also having a wide bandwidth. So bandwidth is where we get a little bit kind of bizarre. That's like when I have like my internet problems at home and they're like, oh, you have, I'm like, what is bandwidth? Like nobody knows what bandwidth is. And that's kind of the same concept here. Like nobody really knows what it does. But basically it is the range of frequencies that we are allowing it to display, right? So if we have a 3 megahertz transducer, well, the system is going to give us some 1 megahertz frequencies. It's going to give us some 5 megahertz frequencies, right? So we're saying that we want to use a 3 megahertz transducer, but we're always going to get something a little bit more and a little bit less, right? It gives us a range where that range is going to be that 3 average. So when we have a wide bandwidth, we are saying, okay, we're allowing this wide range of frequencies to be transmitted. We don't really want that, right? We want more of a narrow bandwidth where we're a little bit more precise in the frequencies that we're allowing in. So when we have the backing material, it's increasing that bandwidth. It's letting that range of frequencies be a little bit bigger than it should. That's all you really need to know about bandwidth. Now, inversely to bandwidth, we have low quality factor, and that's exactly what we're talking about. So the quality of that sound wave being sent into the body. We're dampening it, right? So we're automatically kind of decreasing its value a little bit. We need to in order to control it, but we are decreasing its value. So when we have that backing material, we are decreasing that quality. Bandwidth and quality factor, or Q factor, are inversely related to each other. So when you have a decreased bandwidth, a narrow bandwidth, you have an increased quality factor. So just keep that relationship in mind too. And then just kind of everything that we previously said, decreased sensitivity, that is going to make our transducer less responsive to those smaller reflections that we could be using for clinical purposes. And that wide bandwidth, that is just going to allow more of a range of frequencies to travel through when we don't necessarily want that. Okay, so our transducer frequencies. So everything that we've learned so far has always kind of been geared towards pulsed wave, right? We haven't talked too much about continuous wave, but what we know about continuous wave is that it's constantly going, right? There's no talking, there's no listening. It's just always talking and always receiving. So we don't use that because that's not the best in order for us to get and process those reflections. We need the talking time and we need the listening time. So our pulsed wave transducer frequencies, we know that these waves are going to create these short pulses during that electrical spike that travels through the wire and strikes the active element. So when we have our system that's operating under pulsed wave, our machine is going to send that electrical pulse to the transducer, and then in the transducer, that electrical pulse is going to hit that active element and then send itself in. So this is very short. So again, like that piano key, you hit that piano key, right? Just a one little quick strike. But then what happens to your sound? Does your sound just stop after you hit the strike? No, it keeps going, right? So we're keeping that pulse duration short, but it's still going to continue traveling. Frequency with the pulse wave is going to be determined by the characteristics of the active element. So how many active elements are we using? What type of pattern are we activating those elements in? Those are all things that we're going to talk about further down the road. Now, continuous wave, we have this constant electrical signal. So we're no longer talking about that piano key signal that we're getting of electricity. We are just having the constant stream of electricity that is continuously exciting that active element. So that active element is just constantly in a state of excitement, right? And it's just like send. There's no time for it to calm down and relax. So the frequency of sound sent into a continuous wave transducer is equal to the frequency of the electrical signal. So there's no differentiation between any of the components or the compartments of a continuous wave transducer. That's like with that previous slide that we were talking about, we don't use backing material in a continuous wave transducer. So we don't have to worry about bandwidth, quality factor, sensitivity. We're constantly sending in a sound wave. So we don't care if it vibrates freely or too long, right? Longer than it should. We don't care about any of that. So we're not going to dampen that original sound wave with a continuous wave transducer. So again, kind of just recapping here, that pulse wave transducer, that's that electrical excitement that just sends itself in a very short strike. It's going to create that excitement in the active element, and then that is what is going to continue to travel. The pitch and the duration of that piano key, right, using that piano key reference, is going to depend on the key that it's struck. So when we have these transducers, we have our active element, there are also these little different compartments from the electrical source that go and excite that active element. So the system, there are things that we can adjust, and there are, depending on the transducer that we're looking at, the system could say, all right, here's my active element layer, right? But then I have all of these little wires that are connecting to different parts of it, and I only want to excite this part of the crystal or the active element, or I want to excite the entire part, right? So these are all things that we can adjust and we'll learn about, but that is going to all depend on what we are trying to do. So we're still sending in that short electrical pulse from our system to excite the crystal through the wire, but we are just saying, do I want to do the whole thing? Do I want to excite some of it? Do I want to excite this side, that side? Like what's the circumstance in order for that to happen? Pulse wave transducer characteristics, these are going to be determined by the frequency of the sound wave. So of course, what type of transducer are we selecting? What type of frequency are we selecting? And that's also going to depend on the thickness of our active element and the speed of sound as it travels through that active element. So we'll just finish up talking about those two characteristics. So the speed of sound in that active element, again, talking mainly just about the pulse wave transducer, no longer talking about continuous wave. The speed of sound in that active element and the frequency of that sound are going to be directly related. So the higher your frequency is, the faster you are going to be able to travel through that active element. And the faster the speed of sound in that active element, that should say PZT, not PZR, you are going to produce a higher frequency to travel through your image. Now, your standard speed of sound for piezoelectric materials is going to be 4 to 6 millimeters per microsecond. So pretty fast, and it's actually 4 times greater than the speed of sound in soft tissue. So we want to have a fast speed of sound because this is where our source is coming from, right? So we want to have it be a little bit faster because if we think, what happens as sound waves travel? They get weaker. So you don't want to already start them off similar to soft tissue because as it continues traveling through soft tissue, it's going to get weaker, weaker, weaker. So you want to have it be a little bit faster when you are originating it in that active element. And then our thickness. So this is all going to vary again on what type of pulse wave transducer you're using. But the thickness of your active element and the frequency are going to be inversely related. So the thicker that active element is, the lower your frequency is going to be. Therefore, the higher or the longer your wavelength will be. So you have a thicker active element, decreased frequency, and increased wavelength. And that kind of just makes sense, right? Because the thicker something is that the sound wave has to travel through, the longer wavelength we need and the lower frequency we need to get through it. Okay, so any questions about any of this? Good.